Okay, this video is looking at the Chapter 1, Introduction to Differential Equations, and Section 1, going and looking at definitions and terminology. The first few problems are going to see whether or not what the order of a differential equation is, and the second part is going through and determine whether or not the function is a linear differential equation or not. And the definition is in the book for what linear is. And the easiest way I can think of to explain it is in terms of examples. So then the second part of the section is going and looking at various differential equations and equations involving derivatives, possibly higher ordered, and trying to verify that various functions are solutions to those differential equations. So the whole name of the game is we're going to try and, here's a differential equation, we were trying to go through and solve those equations for whatever the variable is. So up in problem 1, 4, 5, and 7, we're looking at what's the order and is this linear or not. And so here, when we're looking at the order, I'm going to look wherever I can find a derivative or original function involving the letter y. Okay. And in all three of those instances, there's the original function, then there's the first derivative, and then there's the second derivative, and they're all to the first power, times some stuff involving x's added together or subtracted together. So this turns out to be what we call a second order, because the highest level derivative is second derivatives. And this is an example that's linear, because the stuff that you have here, it's something times y double prime plus something times y prime plus something involving y's is equal to something just involving x's. Okay, so the important thing is we've got, for a second order linear differential equation, you've got a y prime term times stuff involving x's added to a y term times stuff involving x's, and that may have be 0, so there may not be any y prime term, but if there is, then it's just times x's, stuff involving x, and plus something involving just y times stuff involving x, and that's equal to something just involving x. So we're not focusing on the x stuff, we're focusing on the y, the variable, the dependent variable that we're looking for, because presumably we want to have y as some function of x as its solution. Okay. Now looking at the second, number 4, that's the second derivative of u with respect to r, and that's using Leibniz notation instead of Newton's notation with the dashes. That's more common. And then there's a derivatives, and then there's a u here, and then there's a u there. So this is second order. If this hadn't been here, because that's buried inside of a cosine, okay, if we didn't have that u on the right hand side, that would have been a second order linear differential equation. In fact, we would say with constant coefficients, because the stuff involving the u double prime and the u prime and the u are all times just constants. But because there's a u buried inside of the right hand function, that u term, when you go and you look at it, because that's going to be a u minus cosine of r plus u equals 0. When we go and we look at the stuff involving just the u's, just like we had just involving the y's up here, that, because it's not buried, it's nonlinear. And then here we've got a second order differential equation, because we've got derivatives and second derivatives. And this also is nonlinear because of the squaring. This part right here is messing things up, and this part here is messing things up. All right. So now, if we go through and we're looking at this next piece, if we're doing in where the variable, it's a linear differential equation in the variable x or in the variable y. So if we're going through and trying to figure out what this is, if I have over dx, this is just a constant, and I've got a y squared term and a dy, so it's not linear for the y's. And then if we head over dy and a dy, then we have just a dx over dy plus just an x times stuff involving y's, which is 1. And so that would have been linear for the x's being the dependent variable. Okay? All right. So now, if we're going back to trying to solve something like this, if for 11, 13, and 27, we're trying to solve differential equations. And what they're doing is they're saying, here's my answer. And so we're going to plug that in here. And then we need to go through and plug in for y prime. So I'm going to have to take the derivative. Y prime turns out to be, well, the derivative exponential is going to be e to the minus x squared over, e to the minus x over 2. And then you pull out the derivative of the inside, which pulls out minus a half. So now verifying that we have this all plugged in correctly, we're going to have 2 times whatever the derivative was, which we said was minus a half, e to the minus x over 2, plus the y value, which we said was e to the minus x over 2. And that's equal to, so just starting off with the left-hand side, we're going to try and manipulate it till we get to the right-hand side and verify that the left-hand side matches up with the right-hand side in this equation here. Okay. So simplifying that out, we get minus e to the minus x over 2 plus an e to the minus x over 2. They wipe each other out and we're left with 0, so that does in fact check out. Okay. Now with the next one, if I were to take the derivative, because of the fact that this is a product with a chain rule on the inside for each one, the derivative of the first term is going to be a 3e to the 3x, carry along the cosine of 2x. And then the e to the 3x gets carried along. And now we're going through and looking at the derivative of cosine, which is minus sine. So I'm going to go through and change my sign here. And the derivative of the inside is going to pull out a minus 2. And then we've got sine of 2x. So that we're going to plug in there. Just like this y term we're going to plug in here. And now we need to figure out what y double prime is to plug into there. So we're going to have y double prime is now going to be equal to the derivative of all of that. And now, gosh, that's going to be 4 terms because it's 2 product rules. So the derivative of the first term is going to be 9e to the 3x, carry along the cosine of 2x, and then we're going to have a minus 6e to the 3x times sine of 2x from the first term. Then for the next piece, we're going to have a minus 6e to the 3x sine of 2x. And then we're going to have, let's see, the derivative of sine is cosine, so it's going to be plus minus 4e to the 3x cosine of 2x. Now these two terms will go through and combine together, and these two terms will go and combine together. So you have to collect like terms, take those expressions, plug them in for y prime, plug it the derivative in for y prime, and then plug in the original function. And just like we did with problem number 11, simplify that expression all the way out. There's lots of algebra, but it's all doable. Okay. And then finally, this last one, what we're going to go through and do is take the derivative of y prime, because it's a first order linear differential equation with constant coefficients, just like number 13 was a second order linear differential equation with constant coefficients. And the number 11 was also a first order linear differential equation with constant coefficients. I'm going to throw on the word homogeneous for all of them because the right-hand side and stuff involving just the x's is equal to 0 in each of those cases. So you'll hear that terminology over the course of the semester, summer. So now I'm going to take the derivative of e to the mx, and that's going to bring down the m, and I've got m e to the 3mx. So then if I take those and plug them in to the original function, we end up having an m e to the mx plus 2 times e to the mx, and we want that to be equal to 0. So now, because both terms have an e to the mx in it, I'm going to factor that out, and what I end up getting is an m plus 2 e to the mx. And so now I've got a product, the m plus 2 times e to the mx, and we're setting both of them equal to 0, and the only way you get a product equal to 0 is if one of them was 0 to begin with. So either the exponential is equal to 0, or m plus 2 is equal to 0. Exponentials, when you look at their graph, never are asymptotic to 0. They never touch x equals 0. So that forces m plus 2 to be equal to 0, which means that m has to be equal to -2. Okay. So that technique of solving a differential equation is something that we're going to be doing a lot of. It's going to get more complicated, but that approach is going to be something we'll be going through and doing throughout the course. All right. So the next video is going to be looking at section 1.2.